Hey everybody, no video today, it's going to be just the audio, but this is for our notes on just page 16, looks like. Yep, so just page 16, and just a quick little review. Here are the variables for our kinematic stuff. Remember we have displacement, which is given with the delta, meaning change, and x being position. So change in position, you got initial and final velocity right there. Acceleration represented with an A, and time. All right. Next up for us to remember, really important, kinematic equations. We haven't seen these. Remember, you can always just Google kinematic equations and find these. But the three most important ones, okay, we have these right there, and those will come into play here in a little bit. So moving on down to example 9. All right, here we have a 2,000 kilogram car. So as always, as I'm kind of working through this, I like to just kind of either underline or circle some of the important parts. So I got a mass right there. It's slowed down uniformly, which means constantly, from 20 to 5 meters per second in 4 seconds. So, and we are being asked to determine the net force. So right away, I know, all right, it's telling me find the net force, which means, let me get this to like a normal size. Net force equals mass times acceleration. Newton's second law. If I can figure out the mass and the acceleration, all I have to do is multiply those together to calculate the net force. So what do I have? Well, right away, I know I have the mass, which is 2,000 kilograms. But I do not have the acceleration yet. So I need to now put my thinking cap on and figure out, okay, how do I determine, how can I calculate the acceleration? Well, I have all these kinematic values. So let's go back to our kinematic type problems and see if I can actually solve for what the acceleration is. So we'll do that in green. So remember, we make a table of all of our values. So I'm going to go right away, and I know this. So there are all of my given kinematic values, and it's important for me to write the thing I'm trying to actually find, the acceleration. So when I go here, I have all of these variables. I need to look at those kinematic equations and figure out which one of the equations I can use. So right there, that first one I have written is the only one that has all 4 of those variables in it. So now I just need to rearrange this, solve for acceleration, and plug it in. So there is the acceleration, okay? And now that I have the acceleration, I can take this value all the way over there and plug it into Newton's second law to actually answer what the original question was asking me. Which, when I multiply all that stuff together, I end up with net force of 7,500 newtons, and that is negative, meaning that net force would be directed to the left or in the negative direction. Okay, so there's my answer. And this part, we don't need to do that second part. How far did the car go? That's just another kinematic problem. I changed my mind. We don't need to have that part of the example on there. Okay. All right, example 10. There is one additional piece of information you're going to need to write in for this problem. There is no mass included, and we need a mass. So important to know that we're going to say that the mass of the roller coaster and all the passengers in it is a total of 500 kilograms, right? So here we have end of a roller coaster ride. Passengers are accelerated to rest, so they're slowed down to rest. So to rest is the final velocity. Right? They were going 50 meters per second, and it took them 100 meters. So that's the net force. So again, what do we got? Well, we are being asked to solve for the net force. So mass times acceleration, right? We now know the mass of 500 kilograms, but we don't know what the acceleration is yet. So that's where the kinematics come in. So let's figure out and write down all the kinematic expressions that we know. So we have final velocity is 0, initial velocity was 50, 100 meter displacement, and we're finding acceleration. So which kinematic equation can we pick? Go ahead and pause your screen and figure it out now. All right. So what would it be? It would be, there's the equation that we're going to use. So now it just becomes rearrange for acceleration. Plug everything in. So remember, that is not the final answer. The final answer is we need to take this acceleration. The whole reason we are trying to find it is so that we can plug it into Newton's second law. And once we have that, all we have to do is calculate and figure out what the net force is. And there you have that the net force is 6,250 newtons in the negative direction. So that means like if the roller coaster cart was zooming to the right, there's a net force, there's more force to the left acting on that cart, causing it to slow down. All right, example 11, the last one on these examples. It's a three-parter, but it's kind of breaking it down step by step. So there is this thing right here. At this point, we were supposed to have done this lab, but since I'm not there, we haven't done it yet. So here's all you really need to know. To calculate, and it's not going to show up on the next exercises, but to calculate the force of friction, we need to know this thing called mu. And mu, that is the Greek letter mu. And you say it kind of like M-E-W, mu, right? That is a number that basically describes how sticky two surfaces are. So, you know, it's calculating friction, how sticky something is. So it's a stickiness number times the normal force between those two objects. Okay, so that's called a coefficient of friction. And then that big capital N right there is the normal force. All right. So that will rear its ugly head in this picture, or in this problem, but we'll figure it out, all right? So what do we got? We got a football player hits a 75 kilogram training sled. That's a mass. It's got 200 newtons of force applied parallel to the ground. So like if we're looking at that problem, this person's hitting that thing there. We'll call that force. Coefficient of friction is 0.2. So I'll show you that in a second. Draw a quantitative force diagram for this. So our sled is going to be represented by this dot. And just like always, we have a force of gravity going down. This ground is flat, which means that the normal force is going straight up. If I could draw, there we go, straight up. There is a hitting force to the right because we see that player right there is pushing the sled to the right. And then, you know, it's sliding on the ground. So friction's job in the universe is stop things moving. So if it's being pushed to the right, friction is resisting to the left. Okay. Now, the quantitative part means we need to have numbers in all these. So what do we know? Well, the sled is not sinking into the ground and it's not flying up away, right? So these two up and down forces must be equal to each other. So the way we can write that is normal is equal to the force of gravity. And we know a way to calculate the force of gravity. That is mg, mass times gravitational pull. Well, mass is 75 kilograms. And on Earth, G is 10. And usually we actually, instead of meters per second squared, we write that newtons per kilogram. Okay, but 75 times 10 gives us 750. So that means the normal force is equal to 750 newtons. And the force of gravity is also equal to 750 newtons. Now, they originally told us the 200 Newton force is that hitting force to the right. So the only one we now need to calculate is the friction force. So remember we had that equation. The friction is equal to the coefficient times the normal, right? Well, that is 0.2. And the normal we just figured out is 750. So once we calculate that, we get that it's 150 newtons. So I know my friction force is 150. Okay, so now all of my forces have numerical values, which makes this a quantitative force diagram. Okay, part B, calculate the acceleration of the sled. Well, remember, if I know all the forces, Newton's second law tells me I can calculate the acceleration. So in the y direction, up and down, they all cancel each other out. So that's not going to help us at all. All right, so there is no net force in the y, which means all that net force must be coming from the x direction. So we have 200 to the right, 150 to the left. So the net force, 200 to the right, 150 in the opposite direction, so opposite sign. And then it becomes just solving. So we got 50 newtons equals 75 kilograms, which when I finally just solve for the acceleration gives me 2/3 or 0.67 meters per second squared. Remember, that is positive, which means that that acceleration is to the right in the positive direction, which makes sense because when I look at this force diagram, I have more force going to the right than I do to the left. So that tells me this object is going to accelerate to the right. All right. Very last thing it asks, the player maintains that 200 Newton force. So because that same force is there the whole time, it's going to be accelerating the same the whole time for 5 seconds. How fast? That's final velocity, that type of thing. How fast will it be going? So what will its final velocity be if it started from rest? So this is asking a kinematic type thing. So we know the acceleration is 0.67, and then just all of the other things. So once we have this, pick your kinematic equation. It's already solved for final velocity, and so all we need to do is plug and chug. And there you have it. All right. So all these problems is, they tie into each other really well. Use the forces to figure out acceleration or vice versa. Okay. So your next job is to turn the page, and on page 17, there is a practice. None of these practice problems use the friction fun equation or anything like that. So you don't need to worry about seeing that mu show up again, but do your best, and I will have answers posted soon.